So this was the proton acceptor. So therefore, by process of elimination, the proton donor would be the acid. So that donates protons. Pardon? Acids, well, when you say positive. So, no, it depends. So, okay. It depends. Not all acids are positive. So that's a proton. And so in order for them to be able to donate it, it's going to have what's called the dissociable proton. Which I didn't know that kind of terminology before. So that's why Na4 plus has an extra proton that it can donate. By donating it, it's an acid. Whatever it accepts it would be the base. Okay, so for that example, that specific example here, and that actually does bring us up to another good point, just terminology point. So plus H2O. This is just an example. Plus water. Okay. This is ammonium. Oh, whoops, that should be H3O plus. Ammonium plus water goes to ammonia and hydronium. Let me rewrite that. 3O plus. Okay. So, if we look at the left side of the equation there, we can pick out what's going to be the acid. Okay? Which one of those two will be the acid on the left side of the equation? Is it going to be the ammonium or the water? Which one's going to be donating the proton? It's ammonia. Ammonium. Yes. So this one right here is called the acid. This is the base, because it will be what accepts the proton. Now, in this sense, what they do is they call the ammonia, which when you go backwards, it's the base. This is called the conjugate base. In case you read that or you see that anywhere. It's just the base on the other side, the conjugate. So they call those conjugate acid-base pairs. So the ammonium and ammonia go hand in hand. And the hydronium ion, the H3O plus, is called the conjugate acid. I'm going to abbreviate it just because I don't have much space. CONJ. But it's conjugate acid. Because going backwards, it's the acid. And ammonia is the base.
For the base, do you need to put, is OH negative for the base?
Pardon?
OH negative.
That's another example of a base. So, for example, we could say, let me move these up. Whoops. Oh, let's see. That's supposed to be a minus. It's not very well. So we have OH minus, which is hydroxide. And by the way, CH3COOH, that's the chemical formula for acetic acid, which is when you dilute it, you have vinegar. That's one way to make plants. At least biologically relevant. Goes on to make water and acetate. I would never ask you, okay, draw acetate. No. Organic chemistry, biochemistry, yes. Not here. So if we look at this example here, is the OH minus going to be the proton donor or the acceptor here? It goes from OH minus to H2O. So did it donate a proton or did it accept a proton? It accepted it, and so does that make it an acid or a base? It's a base. By definition, the other one has to be an acid, but you could still go ahead and do it. See, it has that extra H here. It lost it there, so therefore it had to be the acid. It becomes what's called, the conjugate base over on this side. and water is a conjugate acid. I'm just going to abbreviate. Because I could have drawn it going the other direction, with the water and the acetate on the side, and the acetic acid and hydroxide on the other side. That's why they just call them conjugates. What was the base becomes the acid, and vice versa. Okay. What was the pH at which it changes over from acid to base, and vice versa? So what's neutral pH? 7. If it's less than 7, is that an acid or a base? It's an acid. If it's greater than 7, it's a base. Okay. All right. So one thing I wanted to do now is just show you, and you may want to practice this with your calculator so that way you feel more comfortable with it, is just if I gave you either concentrations or pHs for you to know, okay, that's going to be an acid or a base. Which is it can be simple. Like if I said it was this, 3. Let's say, well, I'll do 2 examples, or 3 examples. Okay, I'll give you a moment to get caught up. And I just ask you, and no, under these conditions, are we talking about is it acidic or basic? So the first one I gave you the pH. Next two, you'd have to figure out the pH. Even though if this was on the quiz or exam, and I just said, is it an acid or base? I'm going to show you a easy way to say, okay, it's acidic or basic. I'll also show you how to figure out the pH, but just to get it and help. Let me move these other stuff out of the way. Okay. All right. So the red, I think it is that acidic or is that basic? It's basic because it's greater than pH 7, so it's basic under basic conditions. But you may not be able to tell directly for the ones that blue and white, the blue and white one. Some people may. But I just wanted to review what pH is. So pH literally means negative log base 10. So sometimes, I think that's, on most calculators, it probably just says log. That's what mine does. Of the concentration in molarity of the proton. The H pluses. So one thing you can do is to go ahead and just put that into your calculator. That's why I suggest that you practice some. Because I know each calculator kind of is a little different. So over here, we'd find it, we'd go the negative log base 10 of parentheses 3 times 10 to the minus 12, which is equal to, oops, I'm really needing batteries. Okay, so we have negative log parentheses 10 to the minus 12. Yep, okay. And so we get 11.52. You may round it a little bit different. Negative log. So it is base 10 automatically on yours, because yours just says, a lot of them, if I don't mind me use this, a lot of these, because this is a TI like mine, for the base 10, the default LOG is a base 10. I think now some of them may say LOG 10 or something like that, but no, it's just default. Whereas if it says LN, that usually is not default, that's the default of a logarithm based off of E. You just want to avoid that one. Okay, so there's nothing in this class that we use the natural logarithm. That's a natural logarithm. We don't use that for anything in this class. I do for biochemistry. So, just given 11.52, is that going to be basic or acidic? It's basic as well. Now, I'll show you, like a way to save time if this was on the exam, and I didn't ask you to actually figure up the pH. I just asked you, is it basic or acidic? It's not a cheating way, but the quick and easy way is look here at the exponent. Because if you look at that exponent, you take the opposite, which is the negative, opposite of that exponent, and it's going to give you a rough idea. So we know that this one should be somewhere around 12. Because it's negative 12, so it's going to be somewhere around 12. And lo and behold, it's 11.52. So using that, it's not cheating way, but that shortcut way, the one that's white, is this one going to be basic or acidic? It's acidic because it's to the negative 2 power. So when you take the negative log base 10 of it, it's going to be somewhere roughly around 2. Okay. But if the question had asked you to solve it, you actually would solve it like this. 2, 5. Whereas if it just asked you, is it acidic or basic, you can eyeball it based off of that exponent. You just have to remember to take the opposite, the negative, because it's negative log base 10. Let's see, I forgot what it was. 1.25 minus 2. And it's 1.90. So once again, and that's also even if I did ask you to solve for the pH, that's a good way to check to make sure you entered it in your calculator correctly, is to see if whatever number you got is around the opposite of this number right here. It's going to be a little, now if this was a 1 times 10 to the minus 2, it really would be negative 2. The reason why it's a little off from that is because it's 1.25 times 10 to the minus 2.
When you gave us the pH like 7.3, are you going to ask us the concentration of?
So I could, and it's even easier to do. Okay, so let's do that one. Let me move all this up a little bit out of the way. Okay, so let's say that you were given pH 7.3 and I asked you to find the concentration of it. You literally, all you have to do is you would write 1 times 10 to the minus 7.3. Or that's the best way. Okay. That's fine. Oh, I've got a bracket there. Well, maybe not. Maybe it's never mind. Sorry. Okay. That's it.
So then why, if it is that simple, why is 3 times 10 to the negative 12 11.5?
Because of that 3. If this was a 1,
It would be itself.
it really would be itself. But that 3 really is 3 times that. It does throw it off a little bit.
You said that's asking for the.
That's if I was going backward. Yeah, so literally that would be, here, let me write it all the way out. Whoops. Just a second. Let me erase that a little bit. That's molar is equal to the concentration H plus. I think literally that's what that means, yes.
So is that one of the formulas that we're going to have to know?
I mean, yeah, I would know what negative log and pH is, because it's not really a formula. It's like plus and minus and addition and subtraction. But I plan on giving you guys molarity and molality. Like what molarity is, moles per liter, molality is mole per kilogram. There's not a lot of formulas and stuff on this. So. Okay. So now I wanted to give an example. I shouldn't say about one, but one that's has many more steps. Okay, so I'll write it out. This is just an example. How many milliliters of 0.13 required? think everybody knows to get caught up. Something like this is probably about as difficult, once again, not so much difficult, but as time intensive of a problem that you're going to have. There are multiple steps to it. I should say that you can have from this chapter. I can only think of one. Well, yeah, I'll do another example for this. One nice thing about the neutralization reactions is typically, I can't think of any exceptions even off the top of my head, the stoichiometry, the ratio is always going to be 1 to 1. So literally one acid plus one base neutralizes. You know, if we went back to the last exam, we had to do the the net ionic equation. You'd find out that this equation would literally be H plus an OH minus makes water. So it's 1 to 1. And I would give you the fact that molarity, you may need to recognize a capital M as molarity. Molarity is equal to moles of solute over liters of solution. Which, remember, a solution is solute plus solvent. That would be given probably on the very first page, if I can remember. But they're not even given in the problem. I guess you could always ask, like, how many grams instead of milliliters? Do we have to go to moles to grams? That's another way of asking. There's only so much that you could ask. Okay, so if I wanted to write out the equation, or if you were asked to write out the equation, so I'm sure you all want to, right? It's HCl plus NaOH. They just swap partners. Makes H2O plus salt. And if you remember, this doesn't matter. This is not what it's asking. It's just a salt. That's just the balanced equation. Okay, so what we're going to need to do is have a plan of attack. We're given a volume and a concentration for the acid, and we're given a concentration of the base, but it's saying how much the volume is needed to neutralize it. So these are in moles. So the first thing that we need to do is figure up how many moles of acid we actually have. And to do that, so first we need, oops, I thought I was writing. First step is to determine, and I don't know if I told you this or not, but they abbreviate mole. You know how we abbreviate centimeter as cm? They abbreviate moles as mol. You know, they drop a whole E. You know, it's not a big abbreviation. But determine the number of moles of HCl. Because that's going to let us know how many moles of base that we need to have in order to neutralize it. So, now let's do that. The problem gave us this for the HCl. That's the exact same thing as saying 0.25 moles of HCl in 1 liter. All right, that's the exact same thing. So now we just have to figure out how many moles that we have. So I'm just going to rewrite it to give myself more room. Moles of HCl is in 1 liter. So that means we need to put liters up here. So that way, the whole idea is we want to cancel the liters out to only leave moles. So if we go up here, how many liters of acid do we have? Is this given to us in liters? No, it's in milliliters. So we'll need to first convert that from milliliters to liters. Some of you may have already figured out to do that. You just move the decimal point over 3. If you need to write it out, feel free to do so. It's going to be 0.125. We'll just move the decimal point over 3 places. 0.125 liters. So 0.25 times 0.125. And I get 0.03125 moles of HCl. Now, part number 2 is we've got to go from moles of HCl to sodium hydroxide. So I'm just going to move this over a little bit. Well, actually, I'll make it smaller. That way I can see all of it. I'll move this up. Okay. So number 2, now we have to determine how much, how many milliliters of NaOH. So we know from the equation that if we have 0.03125 moles of HCl, how many moles of NaOH are we going to need to neutralize it? If the ratio is 1 to 1, it's the exact same number. Okay? So that's how many moles of NaOH. I mean, if you wanted to, you could write down, moles of HCl is equal to moles of NaOH. But now we got to go to milliliters. But we were only given molarity up there for the NaOH. So just as a little side note, I'm going to rewrite it. I normally wouldn't do this one this way myself, but just so that way, I got that number 0.13 moles for every 1 liter from that up there at the top where it said 0.13 molar with the capital M. Well, we want the moles on the bottom. So that means we're going to write 0.13 moles of NaOH is equal to 1 liter. But now the question did ask us for milliliters. So I'd say that 1 liter is equal to 1,000 milliliters. If you wanted to solve for liters first and then just move the decimal point over, you can. You multiply by everything at the top, you divide by everything at the bottom. Times 1,000 divided by 0.13. Let me move this up a little bit. The number that I got is 240. Oh, whoops, sorry. That'll make you sick.
Dr. Daisy?
Yeah.
So I set it up a different way and I got the same answer. I'm just wondering if we could go through why that way wouldn't work.
So it probably will. There's more than one way.
Oh, okay.
As long as your
Just
units
like,
cancel out, you're going to be good.
Okay, because I just set up 2 equations where it's moles sodium times milliliters sodium, which was X, is equal to moles HCl times milliliters HCl.
And so that is that N1V1 equals N2V2.
Yeah, that's what
Yeah, that's actually what we did here as well, but we just did it. We solved for N1 first, and then we solved for V2.
So it's okay if I do it that way?
As long as it's, that will always work if it's a 1-to-1 ratio. And for this kind of reaction, it should always work.
Will you ever give us a not 1-to-1 ratio?
I don't think so. Not that I can think of off the top of my head.
Okay.
Okay. Alrighty. Okay. Oh, whoops. Let me finish writing this out. So moles of NaOH. Milliliters of NaOH. Yep. Yes.
Can you explain one more time why the moles of
And let me just move this down. Move this down. Bring this up. So from the balanced equation right here was HCl plus an NaOH makes a water because they swap partners, the H with the OH. Plus salt. Salt we don't have to worry about right now. And so I know that it's 1 to 1. So that's balanced, and the 1 is an I. You could always write out 1, but it literally means 1 HCl for every 1 NaOH and vice versa. So 1 mole to 1 mole, point whatever, 0.3125 to 0.03.
And as you said, you can't think of anything where you went to this one.
Not for neutralization. Now, if I mean, it would be really a hard one to try to think of an example. It would take multiple steps. Maybe for like Chem or organic chemistry or biochemistry, where I said that you have multiple hydrogens and you got to try to get them all off and go. But that would take a long time. More than you could do in 50 minutes, probably. Okay. So let's do another one. But make it a little bit. It's the same thing, but a little bit different, if that makes any sense. What is oops, that's supposed to be well one where I don't know whether I put a space. Because the one other, I guess, good news for you is that this chapter tells you what a weak acid is, but it doesn't really tell you how to use weak acid with what's called a pKa. Okay, which if this was Gen Chem, that would probably be the very next chapter. But the way that this course is set up is it ends with this, to where I guess you want to go on and go on.
Are we going to test on
Pardon?
Are we going to test on pKa?
No. I mean, pK it's related to pH. It literally means negative log of Ka. But we don't do equilibrium constants in internal chemistry, really. Okay. Which is a shame, because that's really important. That's pKa's. And I don't know about your pharmacology class that you guys have to take, but medicinal chemistry, which is related to pharmacology, pKa's are we're talking about. Okay, so now this is a little different. It's taking you it's the same thing, but it's taking it one step further. Okay, because it says what is the final pH, which is a fancy way of saying like how much acid is there, of a solution if 100 milliliters of that base was added to 110 milliliters of that acid. So essentially all you have to do is you've got to figure out how much acid is left over. This time, it's not as simple as saying 10 milliliters and multiply by that number, necessarily. Yeah, if only. But they're different concentrations, or different volumes. So I tried to pick one that was a little bit more complex. Well, the way that I would do this first is you want to, I mean, if you needed to, feel free to write out the equations. The same equation here, HCl plus NaOH goes to make water, plus NaCl, which NaCl, once again, are spectator ions that they're not doing anything, but it's going to be a 1-to-1 ratio. But what I would do here is first determine the moles of both. Determine number of moles of both the acid and the base. Okay. So I'm going to do the base first. You want to convert everything, always convert everything into like the base unit, not base, the generic units of like liters and grams and things like all that kind of stuff. So we want to convert everything into moles and liters. And so to do that, you are given 0.25 moles of the NaOH. Okay, for every 1 liter, so that's what molarity is. And I just multiply that by 0.100 liters, because that's what 100 milliliters is. So that's 0.025 moles of NaOH. I'm going to do the same thing with the acid. Whoops, didn't mean to do that. So if the acid was 0.33 moles of HCl for every 1 liter, convert that to 0.110 liters, because that's how many liters of the acid there were. And that one I can't do by hand. So is 0.0363 moles of HCl. Okay, I give everybody a moment to get caught up. That's like step 1 for everything in moles. But it's asking us for pH. Remember, pH is equal to the negative log base 10. Negative log of the concentration of the acid. And this is a strong acid, so that means 1 H for every 1 chloride is completely dissociated. So we don't have to worry about anything freaky happening. So that means we have to now determine how much acid is left over, if any. Because there are times that you could imagine that the fancy term that they call this is called the titration. You just keep adding base or acid until you neutralize it, or you go over, and see what the pH is. But you could add so much base that you use up all the acid, and then you have to find it based off of the base, which is just one extra step. Okay, so which do we have more of here? More acid or more base? There's more acid, right? 0.0363 versus 0.025. So the base is a limiting reactant. So it's going to get all used up first. We're going to have some of the acid left over. Okay, let me move this stuff all up so that way I can. So step 2 is, if I was doing it, is determine how much acid or base, because if we had more base than acid, then we'd have extra base, is left over. And here we literally have 0.0363 moles of HCl. We subtract out 0.025 moles of NaOH. If there was more base, you put the base on top. And that's going to be equal to 0.03 minus 0 is 3, 6 minus 5 is 1. Okay. Okay. So that lets us know how many moles of HCl that we have that's left over. But now we got to convert that to pH, which pH once again is in terms of molarity. Molarity would be given to you, the equation for molarity would be given to you on the front page or so remember molarity, just because unlike the exam I can't flip back to the first page. Molarity, so I'm going to rewrite it, is equal to moles of the solute over liters of solution. So that's the total amount of liters. So let me move all this up. That way you have my stuff. So for step 3, let's determine the molarity. That's capital M of the protons. If you had extra base, you would be determining the molarity of the H minus. Yeah, to get that pH, you have to do it in molarity. Because literally, when I say molarity, that is equal to, they put the square brackets. That's what that means, which is where you get the, ultimately where we're going to get the pH. Okay, so let's do molarity now of the HCl. How many moles of HCl do we have? Well, we've got 0.0113, just from right above there. Now can be the tricky problem, the tricky part. What's the volume of the solution? What number goes on the bottom here? Remember, it's going to be in liters. What's the volume? You have to add the two together. Literally, this is where, if you're in lab, it's easy for you to see it. But now you can imagine you've got a beaker of glass with 100 milliliters, so you got a beaker of glass with 110. You pour them together. Now you have 210 milliliters, which is equal to 0.210 liters. So it's the total volume. Usually, if I see a mistake, that's probably the most common mistake at this point, is where people would put probably like 0.110 or 0.1, but they forgot they added the two together. It's the final volume. So it's 0.0113, divide that by 0.210, and I get 0.0538 molar. That's the concentration of H plus, or HCl. If you want to write it that way, it's fine. Can't really read my own handwriting. It's 5.3. It's supposed to be 5.38. Okay, but the very last thing that we have to do is convert that to pH. That's why I said that. I wanted to find one that had the most number of steps probably that you'd ever see. So we have step 4, and that's to find the pH, because that was what was asked for in the original problem. So let me move this one up first. So just to review, pH literally is equal to negative log base 10 of the concentration of H plus, which is going to be equal to negative log base 10 of 0.0538. And I get 1.27, and you may get something just a little different based off of rounding. So that would be the final answer. And it should make sense that it needs to be less than 7, because we know it's still acidic because of the fact that we had extra acid left over. If you got something that was like 10, then you know that you probably used something wrong and you got there. But that's